All right, ladies and gentlemen. I know this discussion is interesting, I'm sure. But so recording has started. So last night on the video, you guys got introduced to the idea of projectile motion. Yeah, that's what these things in the table are for. Oh, by the way, I think we discussed the other day that if we have an Alice situation where we have an intruder, those metal bars make good. They would make good weapons. So anyway, you're supposed to run away if you can, but if you can't, metal bars. So, all right. So last night we introduced you to the idea of projectile motion, and we said projectile motion, like it says here, is two-dimensional motion. All right. All of the things that we've done so far up until this point have been one-dimensional motions. And we talked about this ball, and we throw it up in the air, and it comes back down, right? When we talk about one-dimensional motion, right, we're stuck on a line. Right? We can go one way on the line, we can go the other way on the line, but we're stuck on a line. So here, actually, hold on one second. Let me see if I can fix this. Nope, didn't fix it. My pen is not pointing in the spot where it's pointing on the screen because the aspect is wrong down here in the bottom. So I don't know because technology, you know. Whatever. Okay. All right. So one-dimensional motion. We're stuck on a line, right? And that line can either be a vertical line or it can be a horizontal line, or something like this, what we did in the lab the other day, right? Even though this is slanted, so this cart is not moving horizontally or vertically, it's actually kind of moving along, you know, a diagonal line. Because of where the motion detector is, remember we said that the motion detector calls itself the reference point, and it calls everything in front of it the positive direction. This is still a one-dimensional motion because we put the motion detector up at the top of the ramp, and it just moves in front either towards the motion detector or away from the motion detector in one dimension. So all the things that we talked about up until this point have been one-dimensional. And we talked about displacement and velocity acceleration describing that one-dimensional motion. But the real world doesn't work that way, right? And so we talk about things moving in two dimensions. Okay? If you're watching the video, I will try to describe what I'm doing, but you might not be able to see it. So, ball in my hand, right? I throw it up in the air. It comes right back down to me. One-dimensional motion, right? But if I take this ball and in addition to throwing it straight up in the air, I also throw it forward, right? Now it moves like that, where it's moving both horizontally and vertically at the same time. Okay? But one of the key factors we refer to that two-dimensional motion as projectile motion. Right? Objects moving under the influence of gravity are projectiles, and objects moving in two dimensions is a projectile motion. An important aspect of projectile motion is the fact that even though the object is moving both horizontally and vertically, those two motions are independent of one another. They occur simultaneously, but they do not affect one another. So everything we learned about one-dimensional motion still holds true. We just have to take care of it twice. Once in the vertical dimension and once in the horizontal dimension. Does that make sense? Okay. For example. All right. So up on the screen, up on the screen in a second here, hopefully, is a video of a guy on top of a ladder. Okay. And I'm going to pause the class recording while the people in class watch this recording. So this guy, he's going to have two objects. He's going to ask you guys a question. He's going to drop one of the objects straight down. So there's an object that's in his right hand. He's just going to drop it, and it's going to go straight to the ground. The other object he's actually going to throw, and it's going to land over here. Okay? So I'm going to pause my class recording, and then you guys that are in class are going to watch this recording. All right, so intuitively, right? So you said, and this is okay. This is a confusing part, and this is confusing to some people, a lot of people, right? Intuitively, you would think the ball that goes straight down should hit the ground first, because what? It doesn't go as far, right? The ball that he throws horizontally has to travel this whole path on the way to the ground, but the one that he drops just goes straight down, right? But I think we're probably familiar with this idea, right? What actually does happen? Okay, so we'll make our guess here that both balls will land at the same time, and then we'll watch the rest of the video and find out. So the key point here is, like we said, that oh no, it's here. Sorry. That the fact that both of them are occurring at the same time doesn't change one or the other, right? Example. I take this ball, I throw it straight up in the air, right? Okay? And I throw it forward, and it moves in that path like that, right? But if I take this ball and I throw it up in the air while I'm walking, where does it land? Right back in my hand, right? Because of inertia, basically, right? As I throw the ball up in the air, gravity slows it down, stops it, and then speeds it back up when it travels back downward, just like when we did it before. That happens in the second example when I'm walking as well. But what was the ball doing when it first was thrown into the air? It was moving with me horizontally. Gravity affects vertical stuff, but gravity cannot affect horizontal dimension, right? Meaning, is there anything affecting the motion of the ball horizontally? No. Gravity affects things vertically, but not horizontally. So if there's nothing to affect it horizontally, what does it keep doing? What did you say? Inertia, right? The idea of inertia is things do what? We're going to get to this in the next section, but you guys have been introduced to this concept before. Anybody can jump in here. The idea of inertia is that things do what? Stay moving as long as they were moving, right? Inertia is things keep doing what they're already doing, right? Right? Because, yes. So he said, is that why when you throw, like this demonstration of me walking along and throwing the ball up in the air like this, right? Okay? Actually, I should try something. I'm going to try something experimental. Okay? I'm going to try. Let's see if I can do this. I know this is like hardcore. This is like hardcore technology. All right, so.
Oh my god!
It like moves. I can see myself.
Where's the camera at?
All right. Watch out. All right, so we talked about this, right? That throw it up comes right back to my hand. Okay, but if I'm walking, right, it lands right back in my hand as well. Okay, Mohan. Could we do that demonstration while you're driving in the car? Yeah. Sure, right? If you're driving in a car and you got to toss this ball up, where's it going to land?
Back.
In your hand.
Wait, oh, because it's moving with you.
Right?
Oh,
I got it.
That makes sense. Yeah.
Could I do this demonstration on an airplane? Yes. Right? Because, again, it's moving with you, right? Gravity is affecting the horizontal gravity is affecting the vertical motion, but not the horizontal motion. So regardless of what's happening horizontally, the up and down will still happen. Yeah. The vertical part doesn't affect the horizontal part. And it doesn't matter how fast we're going horizontally. Under one condition, what has to be true about our horizontal motion? It can't be, let's go with a more general word, maybe a word we learned in the last unit. It can't be accelerating, right? So if I do this, right? Ready? Okay. Walk, toss, but then I speed up, right? Does the ball still continue to move forward?
No.
Yeah,
Oh.
but it's not at the same rate as me, right? Or if I toss it up and stop, right? I don't catch it because what did the ball continue to do? Move forward, or I stopped, right? Or the third example.
Just change direction.
Yeah. Right? Because those are our three types of acceleration,
Yeah.
right? So if I go here, right, I throw it up in the air, but I turn, right? It doesn't land in my hand because the horizontal motion continues on, because once it leaves my hand, the only thing affecting its motion is what? Gravity. And gravity affects things in which dimension? Vertical, not horizontal. Right? Okay? So, hopefully this works and doesn't just look like a big black screen.
Bye.
So, let's do this.
Can we access that online?
This?
Yeah.
I can get you access to it. This is the Apple book.
Oh,
Okay.
never mind. I don't need
So-
access to it.
All right. Because of where we are time-wise, I actually want to go. I'll show you some more videos on Monday to reinforce this fact. But what I wanted to do is actually see how this affects this idea of the independence of vertical and horizontal affects the motion of an object. Let's look. If you have your IB book, your paperback book, we're going to be on page 43. If you don't
It's in my
have your
locker.
IB book, I have this problem right here.
Okay.
And like I said, this is on page 43 of your IB book. So it says, an arrow is fired horizontally from the top of a tower 35 meters above the ground. The initial horizontal speed is 30 meters per second. Assume that air resistance is negligible. So, 3 parts. The time for which the arrow is in the air, the distance from the foot of the tower which the arrow strikes the ground, and then the velocity at which the arrow strikes the ground. So let's take the first part. Alright, so for part A. Now, when we do these problems, this is what I would recommend. Okay? There are 5 things that we use or that we measure in order to describe the motion of the object, or of the motion of an object, right? Do we remember what the 5 things are?
Yeah.
What are they?
I know it.
Displacement, initial velocity, final velocity, and acceleration, right? Right? Those are the Suvat, right? Those are the 5 things that we can measure to describe the motion of an object. Okay? But now that we have this arrow being fired from the top of a tower, right, I'm going to draw myself a picture right here. Okay? Yeah, I'll draw it down here. So here's the tower. Here's the ground. Just because I didn't draw it down far enough. Because remember I said that my pen and where it's hitting the screen is not lining up. So, all right, and then up here, there's a guy. Sure. Hold on a second. That's not good. I gotta do like this here. Well, the way that it was being held was not representative of bow and arrow. So there you go. How's that? I probably should have drawn. Hold on. One more thing.
What's my ponytail?
That's you.
Oh yeah, I don't have a ponytail.
Okay.
Oh, I don't have.
That's a pink string on the bow, like you so.
Oh, I might like it.
Yeah.
Because you.
Okay. And then Thanks. And then we'll go purple for the arrow. Okay, so. All right.
You associate girls with pink and purple.
No, I just picked pink and purple. I was actually looking for colors that would stand out that aren't red and blue because I'm going to write in red and blue later on. So, okay. All right, so it says that this arrow is going to be fired. The initial horizontal speed is 30 meters per second. So the arrow, Cindy's going to fire this arrow. Oh, man. Wish I didn't do that. But anyway, going to fire the arrow horizontally. But as soon as it leaves the bow, what starts acting on it? Gravity. So even though the arrow is fired horizontally, will it follow a horizontal path?
Yeah, and vertical.
It won't follow a horizontal path. It has to go horizontally and vertically, right? Gravity's going to start pulling it which way? Downward. So what shape is it going to make?
Like that. Half parabola.
Right? It makes a half parabola, like this. Okay? Because that horizontal motion continues as gravity is pulling it down to the ground. Okay? Good there? So this is the setup of our problem. Part A, the time it takes for the arrow, or the time in which the arrow is in the air. So, if we go over to our chart over here, right, we said that there are 5 things that we can use to measure or describe the motion of an object. But now that we know this object will be traveling horizontally and vertically, we have to address these 5 things in both dimensions. Right? So I've written suvat here. That's actually going to be the middle of a table. And there's going to be 2 columns to that table. There's going to be a horizontal column and a vertical column. We need to address these 5 things both horizontally and vertically, because those 2 things are happening at the same time. But they are independent of one another. Okay? Good there? All right. What is question A asking us for? Time. And time shows up down here at the bottom. But which time? Both times. Time is the only special one in this list. And the reason that time is special as far as this table is concerned is because it's traveling horizontally and vertically at the same time. Sorry, I shouldn't use time. They're occurring simultaneously, meaning the time is the same. This time here and this time here have to be the same. But that's the only row in this whole table that has to be the same horizontally and vertically. Sometimes we might find other times that where they are the same, that's more coincidence than anything else. Okay? So, we actually have 2 options here. We can either find time horizontally or find time vertically, and we'll still find the time. And if we find time in one column, we automatically know it in the other column because those 2 motions happen simultaneously. They don't affect each other, but they do happen at the same time. Okay? All right. Now we start filling some things in this table. There is one row that we can fill in right away every time we do a 2-dimensional problem, or at least 2-dimensional motion problem. And that row is acceleration. We said that there is only one force that is affecting the motion of this arrow once it leaves the bow and arrow, or once it leaves the bow. And what is that force? Gravity. We know the acceleration that gravity causes, right? It's what? 9.81. Here, we probably would call it downward just because the upwards downwards thing, right? Okay. And that means that vertical acceleration is going to be negative 9.81. But that's only the vertical acceleration. What is the horizontal acceleration going to be? Somebody said it. Once it leaves the bow, what's the only thing affecting it? Gravity. Gravity affects things vertically. Is there anything to affect them horizontally? No, especially if we say there is no air resistance, which all of your problems are going to be that way for this point, right? And that means if there's no acceleration, what does the object do horizontally? Keep going. Or that's what? Inertia, right? So acceleration is always going to be 0 horizontally. These two things will always be exactly the same in every two-dimensional motion problem that we do. Okay? All right, now let's go here. Okay? So it tells us the initial horizontal speed is 30 meters per second. That means we can plug 30 in for here. That's the initial speed in the horizontal dimension. What's the initial speed in the vertical dimension? If it's traveling horizontally, is it traveling vertically? It says it was shot horizontal, right? If it's shot horizontal, there is no vertical speed. Just like when we dropped the ball, right? Just like the guy on the ladder. He dropped the ball, so vertically its initial speed was 0. He threw the second ball, but he threw it horizontally, meaning that vertically it wasn't doing anything. And that's why they hit the ground at the same time. Because vertically, they both started with 0 initial velocities. Right? So for this object, even though it was initially moving when we shot it, it was moving horizontally. The 30 goes there. Right? Then, one more piece of information. Okay? That goes there. Okay? From now on, we can use Suvat equations, but we use Suvat equations separate sides. Homework for the weekend. It's on the calendar. Answers are posted. Check it out.
I feel like I need to do the homework for this one.
What?
I feel like I need